In this video, I'm going to cover double slit interference. This is found in both topic 4.4 and 9.2 in the IB Physics Syllabus. That means that it's partially SL and HL material. Please take a moment to read the success criteria for this video. Okay, one of the first things is I really do recommend you watch the video by Veritasium on the original double slit experiment. There are so many things that he talks about, including the use of white light in this double slit experiment and its effect, that I really think are important and worthwhile. He starts off in one of the examples of the idea of making two sources in water. And we can see that these two waves are going to interfere with each other. And you can see then very clearly places of constructive and destructive interference. Now, if we use a regular light bulb, we need to have coherent waves in order for us to get interference. So one of the most common things for us to do is to take our light source, have it leave through a single slit, and then the wave fronts that will be leaving from the single slit and landing on my double slit then will be coherent. So you can see that they're in phase here and they'll be in phase when they land on our double slit. So take a look at the appearance of the screen. Notice that these fringes are all equally spaced apart. We don't have an extra wide central maximum like we would if we had single slit interference. One other thing I want to point out is that we're going to be assuming right now that this slit here is very small in comparison to the distance between the two slits. That's so that we don't have to think about single slit interference in this video. That's why this is also in 4.4, which is the SL version. It's only the HL that has to deal with the idea of what would happen if these were wider slits. Okay, so let's think about what's going to happen here. First of all, let's take one wave, and I'm drawing it as a ray, from the top slit and one ray from the bottom slit. And I'm going to point it at the position of our first maxima. Okay, so for those of you in HL, please pay attention. This is for constructive interference. Now, as soon as we're talking about constructive interference, and you can see on this diagram that this ray here, the one at the bottom, is going to have to travel farther than the top one. And the amount that it's going to have to travel farther is going to be lambda for constructive interference. That means if this one started off at this point, let's say right now in time, it is a peak, and it gets all the way here and it's a peak. Well, in order for this peak to be back in phase and being a peak at the same time, how much farther will it have to travel? One whole wavelength. Okay, so that means we have a path difference of lambda. Now, if we want to take a look at this triangle here, and I'm just going to draw it a little bit larger for us. So the hypotenuse is going to be little d. That's the size of the distance between the center of the top slit and the center of the bottom slit. Also, the angle here between this line here, which is perpendicular to where my two slits are and my screen, this angle here has been labeled as theta. That's going to be the exact same angle as right here at the top of my triangle. Now, if I look at this, I can use some trigonometry, and I can see that compared to theta, lambda is my opposite, d is the hypotenuse, so that means I have sine theta is going to be lambda over little d. Now, if I look at the actual diagram here with this lambda, I can also see that that is S. S is going to be the distance between my central maximum and my first bright maximum. And D is the distance between the slits in the actual screen. So I could also write that sine theta is also S over big D. And if I put those two equations together, I have S over big D, lambda over little d. Moving that around is the equation we're going to get from our data booklet. Now, one last thing I want to point out is that why we will always get a maximum in the center, right here. Now, my picture is just down a little bit too low. But if you think about this point right here, right in between the two slits, that means the light from the top one and the bottom one are going to travel the exact same distance. That means there's a path difference of 0, which means they will be back in phase no matter what. So we always have a central bright point. Okay, so let's try this out with a multiple choice question. Fringes are formed on the screen, so you have a single slit which will make our light coherent when it lands then on the double slit, and we have a screen farther away for us to see the light. Remember, light doesn't, you can't see it unless it interacts with matter. So that's why when you have a laser pointer, you don't see it until it hits the screen. So we've got a certain distance, and it says that the distance between successive bright fringes, that's our letter S, is 4 millimeters. So now we make some changes to our design. The double slit is replaced by another double slit which has half the spacing. So that means little d is now going to be d over 2. And the screen's moved so the distance is doubled as what it used to be. Now if I put all of this in my equation, remember S equals lambda big D over little d. If I now put my changes in there, and here's what I get. I get something that's 4 times bigger than what it used to be. So if my distance between the fringes used to be 4 millimeters, now they're going to be 16 millimeters apart. Okay, let's try one more question. So now we have light shining on our double slits. It says the slit spacing was 0.56 millimeters. That is going to be our little d. The distance across the 4 fringe spacing was 3.6 millimeters. Now this is a really important thing for us to think about. The fringes are equally spacing, and why would they measure 4 of them? The answer is so that the percent uncertainty is going to be less. It's kind of like in simple harmonic motion. You didn't measure the time it took for one oscillation of the pendulum. You probably did around 10 and then divided by 10. It doesn't actually reduce my reaction time, but what it does is it lessens the effect as a percentage over the total time, which means each oscillation then can be calculated more accurately. And it's at a distance of 0.8 meters from the slit, so that's capital D. Calculate the wavelength of the red light. Let me put in the numbers. So notice that I wrote them all in meters. It's really important that we keep track of this, so that my final answer is 6.3 times 10 to the minus 7 meters, which is 630 nanometers. And that is in the visible light spectrum, so perhaps I've got a good answer. And yeah, it's pretty close in the red wavelength. So part B, describe how the fringes would differ if white light would be used instead of red light. And this is one of the reasons I suggest watching that video, is you'll be able to see it more clearly. Because white light is made up of many different wavelengths, what happens is then, as you can see with our equation, they should appear at different points. The central one, if you remember I said that, is always going to be the same difference from the top and the bottom slit. It's going to still look white. All wavelengths will then constructively interfere at that point. But red light has a different wavelength than blue light. Blue light, higher frequency, smaller wavelength than red, which means it's going to be a shorter distance for them to destructively interfere. What we will find then is that on the inner edge of the first fringe, compared to the red, we'll see blue. So in the center, it's going to look white. At the next fringe, the inner edge will be blue, then red, and we will, after the first fringe or so from the center, start getting things a little muddled because we're not going to have, for every single fringe we would have had, a nice pattern. Take a look at the video. He has a really good demonstration of this. So reread the success criteria, and now I hope you can agree with all of them.